Okay, we have now a lot of tools. So we are going to prove theorems now, deeper theorems. So I will start with a basic theorem due to Kobayashi. Rather than a theorem, it's an observation. It's easy, of course, but maybe Kobayashi didn't formulate in this general context. So let xv be a directed manifold. I assume here that V is a subbundle, say without singularity, although you can still formulate, you will see what is meant exactly. Well, actually, it doesn't matter much. Assume that the dual, actually you can have singularities and then you assume that the dual it's a sheaf, and then you have to make sense what is the ampleness condition. Well, you just take the projectivization of the linear space and do the construction. It's singular, but anyway you have a concept of ampleness, so you actually it could be singular. Okay, assume that V star is ample, which means that the OP of V star of 1 as an invertible sheaf on the singular space P of V star is ample. Then XV is hyperbolic. Okay, so what's the proof? Well, so you are looking at the projection on X, and then the direct image precisely consists of the sections of the M symmetric power of V star. So this is well known to algebraic geometers. I'm not. Maybe I should explain this here. Okay. So when you are on projective space, so you have the tautological line bundle O of 1 on Pn. And then by construction, the sections on Pn of O of M can be identified with polynomials which are homogeneous of degree M on Cn plus 1. Okay, so this can be identified to polynomials which are homogeneous of degree M. Okay, so maybe I explain in more geometric detail. So just take this Pn to be precisely the fat P of V, which is actually the projective space of lines in the dual, that is hyperplanes in V. Okay, so then O of minus 1. So you have a line here. So a point here is just a line, and the fiber of this is that line. Of course, that line in the dual you can consider as a hyperplane V. Okay, but now you want something which is a section of O of M. So it's a dual. So it's something that multiplies. So you take a section in H0 of that projective space, P of V into O P of V of M. So at each point, now you are going to multiply precisely by V star raised to the tensor power M. So now, because this is a tautological line, this sits in O of minus M, and this, by assumption, sits in O of M. By definition, they are dual. So the product is just a scalar. It's just a trivial bundle. So this actually defines. Well, here I'm sorry. Just take a point here. Okay, you don't have a base. Okay, I'm not taking a vector bundle. I'm just taking just a vector space. Vector space. So actually, in this case, there is no point. So it's just a section which is at point corresponding to the point in projective space. Okay. Okay, but now this is a homogeneous function which is holomorphic and homogeneous of degree m. So it has to be a polynomial of degree m. So in general, if it's not just a vector space but a vector bundle, you do this on each fiber. So you do this on each fiber. And on each fiber, you should have such a polynomial. But such a polynomial is, in terms of vector spaces, it's a polynomial on the dual. But the polynomial on the dual is just a section of Sm of V. But here you have one more duality. It's V star instead. So what you get here is Sm of V star. Okay. Okay. But so now saying that the line bundle is ample means that for M large, you have a lot of sections. So you do have a lot of sections of Sm of V star. And now you can define a Finstler metric. Finstler metric now on V. So take an element Xi in Vx. Then you define the Finstler norm. Okay, so you have a lot of sections here. So you pick a family of sections. So sigma j in these symmetric powers. So this is a polynomial on V now. So you evaluate by duality on the tensor power of M. And then you get a complex number. Take the square. And then if you want homogeneity, you have to raise to power 1 over m to get ordinary homogeneity. Okay? Or 2m, maybe. Yeah, square, 2m. But now, because you have a lot of sections, they generate jets, they produce an embedding, and therefore this thing is strictly plurisubharmonic on V, except maybe along the zero section. So just by the ampleness, so the ampleness implies that n is a strictly plurisubharmonic function on V minus the zero section. Just the sum of squares of holomorphic functions. So now, if you take a Brody curve, it's only needed to exclude a Brody curve. So suppose G is a Brody curve. I didn't say x projective here. Of course, yeah, it's ample, so especially x is compact. So you can. So here, yes, because it's ample, all fibers will be degenerate, so this will have no zeros here. Because of I'm coming back to this. So here it's smooth. Yes, smooth. Smooth if you take M large enough, so that for that large M, you don't have common zeros. Okay. And then you have to take even M larger, so that not only they have no common zeros, but also they generate all jets, all one jets. They produce an embedding, so you have all possible differentials. So it has to be strictly plurisormonic. Okay, the DD bar is strictly positive, not just semi-positive. Okay, but then if you take a Brody curve, then the derivative is bounded for some metric. But then you're just considering the function which to t associates just the norm, the Finsler norm of the derivative. Okay, but now it's going to be a bounded strictly plurisobarionic function. Well, it's strictly plurisobarionic only on v minus 0. So the only possibility is that this function is constant and equal to 0, which means that g is constant. Okay, so this is a bounded subharmonic function on C, therefore constant. But because it is strictly plurisobarionic, it must lie in the zero section. So this implies, in fact, that g prime of t is identically 0, and therefore g is constant, and therefore cannot exist any Brody curve. So this is a proof. It's not very satisfactory in the sense that it's not explicitly bound, and also it requires a strong assumption. So, of course, the interesting case is the absolute case. So what I mean by the absolute case is when you take the full tangent bundle, but it's already sufficient to solve completely the case of curves, of course. So if you have a dimension 1, of course, there are 3 cases. The genus is 0, then you have P1. G is 1, then you have elliptic curves. Then in that case, well, the tangent bundle has positive curvature. Here it's flat, so it's Tx is 0, it's trivial. And for genus at least 2, then the canonical, well, Tx, well, the canonical is positive. Tx here is the dual. The dual is just the canonical here, T star x. And this is positive. Tx is negative in that case. So here this is ample. But in higher dimension, actually there are very few varieties which have ample T star x. They still exist, but there are very few ones. And so unfortunately, it gives an answer to the question only for extremely small class of varieties. So in a higher dimension, examples still exist. So examples with T star x ample. Well, you can do exactly as for curves. You take the ball. And then you take a quotient by a discrete subgroup of the automorphism group. And then, of course, you have the Poincaré, generalized Poincaré metric on the ball, which has a strictly negative curvature. It is invariant by the subgroup. So you just have to prove the existence of discrete subgroups with quotient compact quotient. So there exist, actually, a lot of Borel and many people, arithmetic subgroups such that X here, gamma is discrete and co-compact. But these compact varieties are an extremely small class, and therefore you don't answer much by this criterion. Okay, so you want to relax on this very strong assumption of ampleness. So the next step is to reduce from ample to big. So it's a variant. So if V star is what I will say is big in the following sense, but it's not big as a line bundle. It's big in the following sense. That if you look at sections of symmetric powers, then you can untwist by something which is ample, negative. So there exists an ample line bundle, so that if you look at these sections, they will generate the fibers, except maybe along a proper subvariety y of x. For M large. Well, they all vanish. Possibly. So, of course, because A is ample, you can still multiply by A, and you also get a lot of sections of SM of V star. But, so you will get something strictly plurisubarmonic, but now the sections may vanish. So your Finsler metric still has a strictly positive curvature, but it vanishes along that y. So the only thing you can conclude now is that, in fact, the entire curves will be contained in y. So you have essentially the same conclusion, this one, but it's not completely hyperbolic. So the conclusion is that if you look at curves, so then, so I continue with the statement, then all entire curves tangent to that V must be contained in a subvariety y. Okay, y is supposed to be different. So it's almost hyperbolic in that sense. It's not necessary, in fact, to have a Brody curve. It's not necessary to have a Brody curve, so it's a stronger statement. And then the proof is just by the Ahlfors lemma. So proof. So you again construct this Finsler norm. Okay. So you pick sections. But now they may have, so this vanishes on y, possibly, and is non-zero, is positive definite on x minus y. But now it is still strictly perisobharmonic. This is because you have untwisted by something which is of correct sign. So it's still strictly perisobharmonic. Well, the log of this is still strictly perisobharmonic. But now you are more ambitious. You want to prove for all curves, not just Brody curves. So instead, you are going to apply Ahlfors lemma. So now you look at the differential. So you take a curve, you look at the differential. So it goes from Tc to V. But here you have this Finsler norm. So you just pull back. And now you get the pullback will define just a Hermitian metric gamma on C. The Hermitian metric on C. And now you compute minus Ricci. Minus Ricci of gamma. So it's dd bar of this. But actually, dd bar of this is just the curvature. The curvature is strictly positive. And therefore, it's easy to see that you have a constant, which is just the you fix. Okay, because you are on a compact variety, so it's easy to see that it's larger than A gamma. But now it's a contradiction with Ahlfors lemma. So it contradicts Ahlfors lemma because you would have a bound on the radius of the disk where this can exist, and you are on C, so it cannot exist. In fact, you even prove more that you cannot have, with suitable bounds of derivatives, given you could bound the radii. So this is a contradiction. And so you can even generalize a little bit more. Now, you have a weaker notion, which is p hyperbolicity. So for p hyperbolicity, then you look at maps from p-dimensional balls. And then what you have to compute is, again, the Ricci curvature in the Ahlfors lemma. And the Ricci curvature is the curvature, actually, of the determinant. So you have the volume here, but the volume corresponds to the piece power of lambda p. So it's not surprising that what you need is the ampleness of lambda pv. So you have quite similar statements. I will not redo the proof. It's essentially the same proof. So the variance. So if lambda p, so v star, lambda p of v star is ample as a vector bundle, then xv is p hyperbolic. And you can even weaken a little bit. So instead of being ample, you just assume that it's big. It's big in the sense that similar concept, that there exists an A, which is an ample line bundle, such that if you look at sections, now it becomes a little bit more complicated, sections of the symmetric powers of this thing, and then you twist a little bit by negative, This will generate the fibers except on some algebraic subvariety y. So generate fibers except on proper algebraic subvariety y in X. Then actually all if you take a sequence, now you don't have Brody lemma. So what you will prove actually is that if you have a sequence, then it has to converge in the bad way. And therefore, you prove that the Kobayashi is non-degenerate outside of Y. Okay, so the P Kobayashi Eisenman. So then this implies that the Kobayashi Eisenman KP at any point here for a decomposable P vector. So this is an element in lambda P of V. Will be non-degenerate on the complement of Y. And even, well, you have bounds. Essentially by using again Ahlfors lemma. Okay, but then this has a very, very interesting consequence in the absolute case. So just take the absolute case. Usually in algebraic geometry, the absolute case refers to the case when you deal with a variety rather than a family. Okay. When you have a family over a base, it's called a relative case. So you are relative to a base. And here, of course, you can take V to be the vertical. You look at a family, and then you have the total space X, and then you are looking at the tangent space to the fiber. So you are looking at properties of hyperbolicity generically for fibers of a morphism. So what I mean by the absolute case is the case where S is a point. So in that case, when S is a point, it means that V is the full tangent space. So this is the reason for this terminology. Okay. So the absolute case is V is Tx. Okay, so in the absolute case, now I'm taking also the P equal to the dimension. So you get as a corollary that if the canonical bundle, which is a line bundle, is big, so it means that it has a lot of sections even after you twist by something ample, negative. This is the concept known as variety of general type. So this means exactly that in the terminology of algebraic geometers, X is a projective variety of general type. Then actually, well, here, anyway, you have something n-dimensional, so there is no way it can go to something of smaller dimensions. So you're going to say that it's volume hyperbolic here. So it's volume hyperbolic in the sense that the nth Kobayashi Eisenman degenerates at most on something proper algebraic. But anyway, you cannot have large n-dimensional balls of rank n going to the variety, because anyway it cannot fit in this way. So okay, so then Kn, so the volume, Eisenman volume here is degenerates is non-degenerate on the complement of some proper algebraic variety. Actually outside the base locus of your sections. And then you say that X is a measure hyperbolic. So this is one of the rare cases where an algebraic property actually implies an analytic property. So because the algebraic statements tend to be weaker than the analytic statements. But it turns out that here you have a line bundle. So you know very much about line bundles. You know that when they are big, they have positive curvature in the sense of currents. And then you know something about curvature, and then knowing something about curvature is very strong. So it implies hyperbolicity. Strange enough, the converse is not known. So this is a question, a conjecture. The converse should be easier in some sense, but so there is a conjecture by Lang. That actually it should be equivalent. So X of general type, that is by definition Kx big, should be equivalent to X being measure hyperbolic, meaning that the Kobayashi-Eisenman volume is generically non-degenerate. Okay, so if just observe that a consequence of the conjecture is that if you don't take X of general type, so if X not of general type, then it is not measure hyperbolic, and therefore it is not hyperbolic. It's not known either. A typical example is when X is a hypersurface in Pn plus 1, hypersurface of degree d. Then it's very well known to compute the canonical bundle. So the canonical bundle of X, in that case, is classically O of d minus n plus 2. So this is the tautological line bundle of Pn plus 1 restricted to X. So you pretty much know everything about the sign. So when d is large, it is positive. So it should be more or less hyperbolic, well, conjecturally. But if it's small, then it will not be of general type. So if d is less than n plus 1, then it's a Fano variety, and it's OK. So then Kx is negative. This is what people call a Fano variety. And then there is a well-known theory, which is called Mori's theory, which tells you that, in fact, your varieties is covered by rational curves. It's covered by rational curves, and therefore it's not hyperbolic. But then, of course, when d is n plus 2, exactly n plus 2, the canonical bundle is trivial. You get what people call a Calabi-Yau manifold in general. X is Calabi-Yau. And then it is expected not to be hyperbolic. And in fact, there are even conjectures that there should exist infinitely many rational curves of a higher and higher degree. There are even formulas computing a number of projective curves, but although there are formulas, it's not even clear whether these formulas predict the actual number of rational curves. It's not clear that they exist. So somehow you can compute the number, the virtual number. I don't think there exists still a formal proof that this virtual number corresponds to the real number. So in principle, it should be known that it's not hyperbolic and that there are rational curves, but it's not formally, I think, proved. So, okay, so even that simple case is not completely settled. And now there is another. So this is one of the very important conjectures. And now maybe an even more important conjecture. But tomorrow I will prove part of it, but not the full force. It's called the Green-Griffiths conjecture. Maybe Lang. So I will state a general form, or maybe not tomorrow. Tomorrow the general form, the special form today. Okay, so assume that X is of general type. Okay, so Kx is big. Then there should exist a proper algebraic subvariety so here we are in the absolute case, such that for every entire curve, then it has to be located in this subvariety. So in other words, it cannot be Zariski dense. Of course, you cannot do better, because if you have a projective variety, you can always blow up points. And then if you blow up a point, you create a projective space Pn-1. That Pn-1 will contain a lot of rational curves. But it doesn't change the fact it's of general type, because the fact of being of general type is a birational property. So it's not modified by blowing up. So you cannot expect, with this assumption, you cannot expect better than this. So if both conjectures would be true, you would have a nice statement. So I don't know whether I should call that a theorem or a conjecture, but as I will state, it will be a theorem, although a trivial theorem. So assume that conjecture 1 and conjecture 2 hold. I expect conjecture 1 to be not so difficult, because somehow we proved the difficult part. And the difficult part is easy enough already. But, well, OK. Conjecture 2 is probably much harder. Then a projective variety X is Kobayashi hyperbolic if and only if every every algebraic subvariety, possibly with singularities, irreducible, is of general type. So the fact of being of general type is just an algebraic property. You compute the canonical bundle, you compute sections, so it's a pretty well understood concept. Of course, you have to know about all subvarieties, so it's still difficult. But for instance, it was proved by people like Clemens and Clairvoisin. That if you take x, for instance, in Pn plus 1 of degree at least 2n plus 1 and x generic. So here you can parameterize by, it's just given by one polynomial. It's a hypersurface. So it's parameterized just by the coefficients of the polynomial. So you assume that the coefficients are generic. So you avoid some algebraic subvariety in the parameter space of the coefficient. Okay? X generic. Then X satisfies this property. Then X has no algebraic subvariety, which is not, all algebraic subvarieties are of general type. Has this property. The second one, as all y x of general type. Of course, for x itself is clear because it's beyond the bound, so kx is ample. Okay, so if the conjecture were known, then you would know about generic hyperbolicity of subvarieties, so it would solve a lot. So let me prove the theorem. It's not very hard. Okay, so assume x hyperbolic, then of course this is very strong. Then all subvarieties are hyperbolic because if you have an entire curve in the subvariety, then it is in x. So okay, this implies that for every y, y is also hyperbolic. This is preserved by going to subvarieties, but then by long, y has to be of general type. By long conjecture, conjecture 1. Okay, so converse is slightly more involved. So assume the property. Assume for every y, y is of general type. Okay, so now you argue by induction on dimension of x. Now pick an entire curve. Then you apply the Green-Griffiths conjecture, conjecture 2. Then actually f has to sit in a proper algebraic subvariety. So actually f is a map from C to y. But then y, by the assumption, it's of general type. So in case the dimension is 1, we know everything. So by induction on dimension, that y is hyperbolic, okay, because it has no subvariates of general type. So therefore, it's a hyperbolic by induction, and therefore f is constant, and then you're done. So you see that this Green-Griffiths conjecture is pretty strong because it allows induction on dimension. Okay. So now I'm going to introduce the techniques that are needed to prove at least part of conjecture 2, so a substantial part of it. Unfortunately, not everything. So, well. Okay, so the main technique is to use jet bundles. So the simplest thing is the k-jet bundle of X itself. So this is a bundle of k-jets of germs of curves into X. So you pick a point in the manifold, and then you take local holomorphic coordinates. And then, of course, in these coordinates, any curve can be written as an n-tuple of holomorphic functions. So you just view this as a map into Cn, okay, from small disk here in C into Cn locally. And of course, you can assume that 0 goes to X. F of 0 is X. It will have a Taylor expansion. So it starts with X. And then you have the power series. So you have T xc1 plus T square x2 plus Tk xck. And then you neglect everything of higher order. That is, you take the quotient by the equivalence. So you say that two germs are equivalent if the derivatives coincide up to order k. And this is the fiber. So the fiber of your k-jet bundle, J, I put k where? Okay. Now I put k up. So jk of X, the fiber is just this equivalence classes. And of course, you get a bundle by just projecting the fiber to the point X. And then, of course, here you have the coordinate z1, zn. And here you have the fiber is parametrized by the derivatives, xc1, xc2, xck. Maybe I should divide by k factorial. Yes, I would. Okay, but this is in the absolute case. So now you want to describe the same thing when you have a directed variety. So you have xv. So the relative case. So you have pair xv. Assume, for instance, from now on that v is really a subbundle. If it is not, you just argue on the regular part, and then you go to the closure, and then the construction will still go through. But you do it only at regular points. So assume it's a subbundle. Then you pick a local trivialization, where R is the rank. And you pick nabla, a local holomorphic connection. On U. Of course, it always exists locally, because you have a trivialization. You just take the differentials of the components and take the matrix connection to be 0, so it's holomorphic. But of course, it need not exist globally. In general, it will not exist globally. And now, if you have a curve which is tangent to V, I forgot to say that, of course, in this setting, this has to be viewed, of course, in Cn, and then it's repeated k times. But this is maybe bad to view this in coordinates, so you should rather view this here. So suppose you have V, which is tangent to V. Then you should still expand like this. But then the jet is characterized, so the k-jet is characterized uniquely by the iterates of the connection, well, which are just a thing which I want to denote by Cj, but now they are elements in the fiber of V at 0. It's not completely trivial. And then by the choice of a connection, you identify, so I will denote by jk of V. So this is the bundle of k-jets of curves tangent to V. And then what I just said is that the fiber can be identified with the fact that you have k derivatives here. So this is an element in V k times. However, this isomorphism is not canonical. It depends heavily on the choice of a connection nabla. So it's not global. It's only local, depending on nabla. It's not completely trivial, because it means that given an arbitrary distribution of subspaces without any integrability condition, so you have a distribution of subspaces which varies. Okay, you have X here. You can prescribe freely the k-jet by the derivatives by the connection and still get an integral curve with this given jet. To do this, you just choose coordinates. So you take this to be horizontal by some coordinates. Here you have CR, Cn minus R. And then actually you identify V to the, you have trivialized V here. And then solving this tangency problem amounts to solving ordinary differential equations that, namely the coordinates here, the coordinates, so you have Xi double prime here and Xi prime here. And the Xi double prime should be a linear function depending on x of so this is the defining matrix for Vx here. And then solving this means that you have a curve such that the derivatives for j larger than r plus 1 is something like sum of, or maybe fk, oh j, okay, is the sum of a jk of f of t times fk prime of t. And now k is only for the first component, so projection, the projection on the trivialization. So you can choose freely the first R components, and then you get the other ones just by integrating. So there is no abstraction. You use a Cauchy problem as the initial data. So there is a unique solution. Okay, so this proves this. Okay. And now, essential observation that you have a C star action here, or even bigger action. In fact, there are two commuting actions. Which are of interest. Okay, so you look at the curve. But then you can reparameterize. So you have a change of parameter, tau maps to t equal p of tau. Then you have your curve, t maps to f of t in the variety. And then, of course, you can apply, on the other side, you can apply, for instance, a chart. So you are going to use coordinates. So you go to some open set in Cn, say. So this is a coordinate chart. But of course, the coordinate chart is not uniquely defined. It is defined up to a bilomorphism, up to a bilomorphic change of coordinates. So you may have here to compose with some map C, which is essentially a change of coordinates. You have no predefined coordinates in a variety, so you have to be prepared to change coordinates. Okay? So this is a bilomorphic change of coordinates. But in any case, I'm more interested in the change of the parameter t here. So you have an action by a group, and the group which operates is the group of k-jets of bilomorphisms of C at the origin. So I will denote by gk. So it's some kind of universal Lie group. So it's the group of bilomorphisms which are reparameterization of the curves, but locally. So of course it has to be of the form T maps to A1 T plus AK to the TK, and then I completely neglect, because it's a K-jet, so I completely neglect the higher order terms. Of course, if you want this to be a bilomorphism, you have to take A1 to be non-zero. C star. So this is a group. And of course, it contains in particular the group of homotheties. So just a linear change of coordinates. So in particular, you can take, so you have a subgroup, which is a C star. So it's of course a k-dimensional Lie group here. You have k complex numbers. So this is a k-dimensional Lie group, algebraic group. Which is, however, not reductive. It's not a reductive group. So from the viewpoint of representation theory, it creates difficulties. So it's not a reductive group. In fact, so you have C star, which is a subgroup. Okay, it's just the homotheties. And now the quotient of GK by this subgroup is an nilpotent group. So it's certainly not reductive. Anyway, so as I said, you have an action. So this group acts on JK of V. Simply, if you have a reparametrization and a curve, then you associate the reparametrized curve. Especially because C star is a subgroup, C star operates also, therefore. But now this action is very simple, of course, because if you look at the Taylor expansion, then you neglect higher order terms. Then you just replace T by lambda T, okay? Maybe a factorial here. So you get T lambda Xc1 plus etc. plus Tk lambda to the K Ck over K factorial. So the action, the C star action, the C star action is just in coordinates the action of a lambda on an element which is trivialized locally by the connection as a K tuple in Vk is just lambda Xc1, lambda square Xc2, lambda K Ck. Now, it is interesting to take the quotient by the C star action. So this is called the Green-Griffiths bundle. Which, of course, depends on V. I will put GG for Green-Griffiths because I'm going to define another one. So it's just the quotient of this JK of V, but you remove the constant sections. So the constant section means that all X's are 0 here. So remove 0. It means removing constant germs. And then you take a quotient by C star. So now it's not exactly a projective space because a regular projective space would have been by taking lambda on each coordinate. So it's what people call a weighted projective space. So the fibers here, the fibers are weighted projective spaces. So it just means this. So you take locally, so locally this is of course CR. And you take CR, CR, CR. And then you take weight 1, 2, K. So actually notation, this is, you have the weight 1 here, but it's repeated R times. Because here it's actually not C1, but C11, C1R. Okay, and you have the lambda action on each component of CR. So you repeat R times the weight 1, R times the weight 2, etc. It's a weighted projective space. It's compact. It's a singular space with quotient singularities. And then, exactly as on projective space, you have an O of 1 bundle. Or rather, an O of -1 bundle, maybe. Well, maybe I introduce the rather the sheaves. Okay, so let me put xk as a simplification, or xk Green-Griffiths of M. So in fact, this is the sheaf of polynomials on the fibers that are homogeneous of degree m with respect to this weight. So this is the sheaf. Well, not on X. It's a sheaf on the projective space. Okay. Okay. This is canonical sheaf. Okay. Maybe I draw a picture. Okay. So you have the this projective space here. Then you take an open set. If you're on an open set, of course, the section need not be polynomial. There are polynomials if only you take on the global thing. Then there are just holomorphic functions that are homogeneous of degree m with respect to the C star action. So it's the sheaf of holomorphic functions on jk of v, say h c1 ck, which are homogeneous of degree m. That means that if you consider the C star action, then what we'll get out is lambda to the m. This is for a conic, for an open set in projective space, which corresponds to a cone here in jk of v. And of course, if you take the cone to be everything, the only global holomorphic functions on some Cn which are homogeneous are polynomials. So if you take the global ones, you get polynomials. So as a consequence, what do you get as the direct image. So if you look at the direct image of this sheaf by the projection, so you have the projection, of course, from the jet bundle to X, means now you are looking at the inverse image of open sets here, so you are considering the whole fibers. Okay, so you are looking at the whole fibers. So what you get here this is the sheaf of things which can be written as polynomials which depend, of course, on the base point and are now polynomials with respect to the fibers and are exactly holomorphic here in X and polynomial of degree m on the fibers. With this condition. Okay, but what's the interpretation of this? Now suppose you have a curve. From some open set or some disk in C to X, which is tangent to V. And suppose you have such a polynomial here. Then you can plug in a curve as X, and then these are the successive derivatives. So you are going to put here f prime and fk of t. Here I'm abusing notation because there is not an intrinsic concept of a second derivative on a manifold. It depends on the connection or on a trivialization. So I'm implicitly using in this notation the fact that we have trivialized V and used some holomorphic connection to compute the derivative. So by abuse, you need at least a trivialization. And for instance, I'm using the simplest possible way of finding a connection, which is to use a trivialization with CR. And just take the derivatives of the first R components. Okay, so in coordinates, this is, of course, easy to describe. You have a number of multi-indices and coefficients here, which are just holomorphic functions. And then you have monomials. So C1 alpha 1, Ck alpha k. Of course, this is a multi-index notation. So C1 should be viewed as C1 alpha 1 should be something like C1 1 alpha 1 1. C1 R alpha 1 R, because this is an R-dimensional object here. So the multi-indices here are multi-indices of length R, where R is the rank of V. And the homogeneity condition is when you plug lambda here and lambda to the k here, you should get homogeneity M. So the condition is that you should have that the length of alpha 1 plus 2 times the length of alpha 2 plus m times the length of alpha k, sorry, k times the length of alpha k is m. Okay, so as you see, this bundle can be viewed isomorphically as the bundle of algebraic differential operators acting on curves. Depending holomorphically in x, but polynomial in the derivatives. Okay, so there are polynomials in the derivatives, but arbitrary holomorphic here in F. But anyway, it's a vector bundle, which I will denote by EKM. Maybe Green-Griffiths. Well, I would put some V star here to remind that it depends on V. I put a star because it's dual to V. If you have a linear form on V, it's an element of V star. If you have a polynomial of degree m on V, it's an element of Sm of V star. So it's some kind of tensor product of V star. Okay, so I denote V star to remind that it's this duality. The sign of the curvature will be the sign of the curvature of V star, not of V. Okay, this is this bundle. Well, a sheaf, but it's a locally free sheaf. It's just determined by this finitely many coefficients here. So it's just a vector bundle where so it's this vector bundle. Okay. So now what if there are singularities? That is a linear space with arbitrary singularities. Well, then you don't really have trouble, because you can always consider the k-jet bundle of V to be a closed subspace of the k-jet of the full tangent space. But this, assume x is smooth, so Tx is a regular vector bundle, so this is well defined. And now you can always take this to be the closure at the regular points. It's completely clear what you are doing. So you just take the closure as an analytic set of the construction that you do at regular points. And then you will get a closed analytic subset, which is perfectly well defined. So you just take this, take the closure of the construction before, at singular points of V. Of course, at those singular points, the dimension might jump, will increase, possibly. But then you can still consider sheaves of functions that are defined on this analytic set and are homogeneous of the correct degree. You still have the GK action, you still have the C star action, so everything goes through. Okay, no. You don't have real trouble. Okay, so I've still about 10 more minutes. So maybe I will introduce now. Here you observe that we made the quotient by C star, but we have a bigger action. You have a bigger action, which is just by all bilomorphisms. So especially, it is very interesting to consider whether these equations, in fact, there is a vanishing theorem I will prove only tomorrow, that tells you that entire curves have to satisfy such equations. So this should be 0 for a lot of such equations. So we will prove actually that there are many such equations under suitable assumptions. But is this really meaningful? For instance, if you are on a variety, is it really meaningful that the second component of a curve is 0? In fact, it doesn't mean much. Because suppose you are on a surface, or maybe first component. Okay? If you are on a surface, you have a curve. You can always parameterize the curve as a graph. So if you have two components, f1 of t and f2 of t, if the curve happens to be regular, the projection on the first component is regular, you can choose as a new parameter tau equal f1 of t, and then your curve will become tau maps to tau f2 compose f1 minus 1 of tau. But then, of course, this becomes linear, and then the second derivative is 0. So somehow, knowing that the second derivative of one component is 0 doesn't mean much. It's not intrinsic. On the other hand, if you know something like, I don't know, the Wronskian, the Wronskian is 0, then the Wronskian means that the derivative of the quotient is 0. Which means, therefore, that the quotient is constant. But the quotient being constant means actually that the curve is a line. So this is meaningful. This has a geometric meaning. So what's the difference between this equation and this equation? Well, difference is that this polynomial corresponding to a Wronskian is GK invariant. So you have so we are going to consider GK invariant polynomials. Well, they are exactly the one that are invariant when you reparameterize. So I'm just viewing them as you can view them like this in coordinates or just as differential operators. It's just isomorphic. So you are going to reparameterize by an element in GK. So you reparameterize, and then you take the derivative. And you want the equation to be preserved. You want to get the same equation on the curve. So it has to be proportional. But proportional factor will be just the derivative of phi to the m. So this is the formula that you want. Composed with a reparameterization. So especially if you take a phi of t equal lambda t, you just get the condition that the polynomial is homogeneous of degree m. And now you see very easily that if you take a Wronskian, so Wronskians, so suppose you take something like f prime wedge So of course this is this belongs to lambda k tx. Well, suppose you compute with respect to some connection. Okay. So it's not exactly scalar valued. So if you want something which is scalar valued, you have to multiply by something which is in the dual. So by a which you will take at point f of t. And A now should be a section of the dual, if you want really a scalar valued operator. So A will be a section of lambda k t star x. So now it depends on A, of course. Now if you take such an operator, it will be a GK invariant operator. Well, let me compute for 2, for instance, just to see what happens. So F composed with phi prime is just phi prime, first year calculus, okay, this. And then F composed with phi double prime F prime composed with phi, plus, then you take derivative again, so you have phi prime square F double prime composed with phi. But now if you take the wedge product, then this second derivative cancels, and then you get phi prime to the cube times the Wronskian that you had, of course taken composed with phi. And of course, having a Wronskian which vanishes has a geometric meaning. It means essentially that your curve lies in some suitable k-dimensional subspace or whatever defined by A here. Okay. Okay. So maybe now I can state, well, and then you're going to consider the subbundle in the Green-Griffiths bundle. So this is the bundle of JK invariant differential operators. So you have a bigger one, which is just a C star invariance. And then you consider in that the ones that are GK invariant. So the GK invariant differential operators. Now I conclude by the fundamental vanishing theorem. So it's due to quite a number of people, so certainly Green-Griffiths. Then the proof was for this bundle was wrong, actually. So I noticed later that it did apply to this bundle. So I corrected the original proof, 95. But then finally, Hsu found a general proof which corrects Green-Griffiths. So after all, the statement is correct, but the proof is not completely correct. So the statement is like this. So for every extremely general for every directed variety. For every ample line bundle on X, for every section, global section, for every P, which is a global differential operator, but you need a little bit of strict positivity in the curvature. So because of this, you have to subtract a little bit of A. And now you only have for all quantifiers, for all anti-curves, tangent to E, then automatically F is a solution of that equation. So it's a bit surprising. So I will not have time to prove it right now, so I will explain related issues tomorrow. So if you happen to know what are the global differential operators that exist on your variety, then automatically the entire curves have to be solutions of this. So now if you want to exclude entire curves, you have to analyze what are the sections of these bundles, where are the zeros of their coefficients, and possibly the zeros of these coefficients will be the y that you need in the Green-Griffiths conjecture. So this somehow reduces the question of studying entire curve to the question of understanding the differential equations on a global algebraic variety. It's expected that it's essentially optimal, that is, that the curves are not constrained more than by this theorem. That the locus, it's expected that the locus of the entire curves is exactly described by the zeros of these equations. So a bit optimistic, but it seems to be like this in the known examples. So tomorrow I will conclude by proving this theorem, which is not very hard, and then giving criteria for the existence of many, many sections, which then prove that you have a lot of constraints on the entire curves, and then I'll give you maybe some grasp on the Green-Griffiths conjecture. Unfortunately, still unsolved.